Welcome. This video says a 4 kilogram 20 degree C sphere with a specific heat of 8 joules per kilogram per degree C is dropped into a calorimeter that contains 6 kilograms of 10 degree C fluid with a specific heat of 4 joules per kilogram per degree C. There's no change in phase. It says show that the equilibrium temperature is 0.7 degrees C. So what I'm envisaging basically is having a calorimeter, a big insulated cup basically, and I have some fluid in here, and I have, let me see how much fluid I have, 6 kilograms, and this is 10 degrees C, and my specific heat equals 4 joules per kilogram degree C, and I have a object, and I'm going to drop the objects into the fluid, and this object is 4 kilograms, and it is at 20 degrees C, and its specific heat is 8 joules per kilogram degree C. That's my specific heat for that. And there's no phase change, etc., etc. Let's put the lid on this thing so that it's a complete calorimeter. This means that no heat can escape or enter the system. It's an isolated system. And so we can say in principle that the change in heat is equal to 0. If no heat can enter or leave the system, then there's no change in the heat within the system. And so I can expand this and look at our two materials, and I can say, well, the mass of the sphere times the specific heat of the sphere times the temperature change for the sphere plus the mass of the fluid times the specific heat of the fluid times the temperature change of the fluid is equal to 0. I just use my definition for specific heat and basically say, well, the heat given up by one of these guys is equal to the heat obtained by the other because there's no change in heat. And so now if let's just move this over here so I can see it. So now if I look at my actual numbers, I can see the mass of the sphere is 4 kilograms, and the specific heat is 8 joules per kilogram per degree C. It's a pretty unreasonable number, but simple for our purposes. And then I want to look at its temperature change. Well, I know its starting temperature, and I want to find its ending temperature. So its temperature change would be T final, always the final minus the initial, T final minus 20. So now let's turn our attention to the fluid. And the fluid, well, the mass of the fluid was 6 kilograms, and the specific heat for the fluid is 4 joules per kilogram degree C. And what's the temperature change for the fluid? Well, its final temperature is the equilibrium temperature for the system. Once the hot bit has gone to if the heat has left the hot object and entered the cold object, that will happen while ever there's a temperature difference, and at the end they'll both be at the same temperature, and this process will end, and that's our final temperature. So the final temperature is an unknown, it's T final, but I know its initial temperature, and its initial temperature was 10 degrees, so it's minus 10 degrees C, and that equals 0. So the heat that was given up by the hot object was obtained by the cold object. And if you look at this, this is going to be less than 20. TF is going to be somewhere between 20 and 10. So this is going to be less than 20. So the red bit is negative. And we're adding that to the black bit. And TF is going to be between 10 and 20. So this is going to be a positive bit. So we have a negative bit and a positive bit summing to 0. And so that makes sense. So if I come here, I can say 3 8s are 24, 4 8s are 32. I have 32 TF minus, it's going to be 640 added to 6 4s are 24, 24 TF minus 240 equals 0. Let's just do it in black from now on. 32 and 24 is 56. 56 TF is equal to, let's take these two numbers to the other side. They're both negative on this side, so they become positive on the other. That's going to be 880. So TF, the final temperature, will equal 880 over 56. TF is going to equal 880 over 56, which will equal 15.71. So 15.7 degrees C. So there we have it. The principle was that in a calorimeter, there's no change in the amount of heat. No heat is let in, no heat is allowed to escape. So the heat given up by the high temperature object is given to the low temperature object, and that continues until they're both at the same temperature. How can I find the heat given up by the high temperature object? Well, it's going to be its mass times its specific heat times its temperature change. How can I find the heat obtained by the colder object, in this case the fluid? It's the mass of the fluid times the specific heat of the fluid times the temperature change of the fluid. I'm careful to recognize that the temperature changes are the final temperature minus the initial temperature for each one. And then I just do my math. So there we have it.